So today we're going to talk about polynomial functions. I'm thinking right off the bat this could be a long one, so buckle down. Here we go. So this ugly thing up the top of the page is a general form of a polynomial. All right, and basically all it is a bunch of coefficients linked to a bunch of variables with exponents. But the deal is your a values have got to be real numbers, nothing can be imaginary, and your n values or your powers have to be non-negative, and the key is integers. Non-negative integers. The degree of the polynomial is basically the largest power of x. So if I look at this first guy and ask, are these all polynomials? I look at that and say, well, are all my coefficients real numbers? They are. Are all my powers non-negative integers? 3, 2. This is actually x to the 0, and 0 is a non-negative integer. So this gives me a yes. That first one's a polynomial. This next one looks all the same until I get to this point right here. What power is 2 over x? Well, this is the same as 2 times x to the negative 1. There's your negative exponent, so no, that's not a polynomial. Last guy, first of all, we've got a rational expression. This we can't even bring to the top without saying that's x minus 3 times 2x plus 5 to the negative 1. That messes everything up, so this is definitely a no. Alright, so what do polynomial functions look like? They're basically what are called curvilinear. Alright, they have curves to them, and they're made of connected lines, so they're continuous, which means there's no breaks. They're smooth, and they're curved. Whereas this is not a polynomial graph. It's got a lot of curves in it, but this little guy right here, this sharp edge, this check mark, if you will, all right, that tells you right there it's not a polynomial, and they call that a cusp. Also, if I have anything, although I didn't represent it, that is kind of piecewise like this, that's not going to be polynomial either, all right, because it's got to be continuous. So there are a few types of polynomial functions. Typically, if I just look at a single term in a polynomial or some ax to the n, we call that a power function. Even power functions are going to look something like a parabola, although as you can see, here's my x squared picture. This is x to the 4th, and this is x to the 6th. Notice as my powers increase, my graph rises sharply. Likewise, if I have an odd-looking function, it looks more like a cubic. Here's the cubed, x to the 5th, x to the 7th. And once again, you'll notice the cubed is the flattest figure, and x to the 7th rises the quickest. All right? So just kind of keep that in mind as we look at these things. So let's talk a whole lot about the nature of these different graphs. All right, the first thing we're going to talk about is roots. A root is basically an x-intercept. That's a fancy name. All right, it's also called a zero. Okay, and these zeros, while they hit the axes, they have other properties within the function itself. If I write the equation of this, all right, then every x-intercept is also going to be a factor of the function. All right, so if it was factorable, it would be some kind of binomial type thing. All right, and it's also going to be a solution to the equation of f of x, whatever that function is. All right, now if I have a repeated root, it's called a multiplicity. All right, so any root that hits once, it has a multiplicity of 1. Anything that you see bouncing off an axis, for instance, this hits and bounces, it doesn't go through, then that is going to have a special type of multiplicity. All right, even multiplicities, all right, don't move from one side to the other. They stay on the same side of the axis. Odd multiplicities will go through an axis. So this point here has an odd multiplicity. All right, This point right here has an odd multiplicity, and this point right here has an even multiplicity. What that multiplicity is, I don't know. It could be 13579, 13579, 2, 4, 6, 8, 10, whatever. But we don't know what the function is. All right. Now, points where this graph changes from increasing to decreasing. So I increase and now I decrease. So this point is what's called a turning point. All right. This is a point where it changes from increasing to decreasing. So this green guy is a turning point, like so. Increasing to decreasing, here's another turning point. So these turning points are in green, and also this yellow guy right here is a turning point as well. Now, it's said that if I know the degree of the polynomial, then it has at most n minus 1 turning points. So I notice in here I have 3 turning points. So at most, all right, this is a 4th degree polynomial. Like so. All right. When we talk about end behavior, what we're basically asking ourselves is we're asking when x gets very large, both positively and negative, what happens to y? So I look at this graph and I say, well, as x gets very large, so as my x is going this way, what's happening to my y value? Well, as x increases, y actually decreases. That's the first part of end behavior. Then what I want to look at is what happens when x decreases. X gets smaller. Well, you'll notice y gets smaller as well. So as x decreases, y decreases. All right? And another way to say each of these is as follows. As x goes to infinity, that's like x increasing, y goes to negative infinity. So y goes down. As x goes to negative infinity, as x gets smaller, y also gets smaller or goes to negative infinity. That's end behavior in a nutshell. So what we're going to do now is we're going to describe the end behavior without actually graphing the function. Now I know that what I'm doing is I'm describing, well, what happens is x goes to infinity and x goes to negative infinity. Now, when I think about plugging infinity into an equation, it doesn't make a whole lot of sense because we don't do actual algebra and manipulation with infinite amount of numbers. We can't really get our hands around them. But I do know that when I'm talking about plugging infinity into a cubic or a 5th degree term, that I'm multiplying it by itself 5 times, 3 times, etc., etc. If I multiply infinity by infinity, that's like infinity times infinity in the AT&T commercial, all right? That's ridiculously bigger than 4 infinities multiplied together. So what happens is when you have a polynomial, the only term that really matters is the term with the highest degree. So all we're really going to look at is the 6x to the 5th and determine what happens as x gets very big and very small in this one term. So I notice as x gets very big positively, and I take a positive number to the 5th that's positive, multiply it by a positive number, so y is going to actually get very big positive. Now when I plug a negative number into here, any negative number to the 5th power is negative. I multiply that by a positive, and I end up with a negative number. So as x gets very large negatively, y is going to get very large negative as well. And that's my end behavior. Next, we're going to find the real zeros. Well, the real zeros are basically trying to find out when y is equal to 0. I know y is just f of x, so really what I'm trying to do is solve this equation when it's set equal to 0. So now you'll notice it's already in factored form, which is nice. All right, and I notice that I have a zero product principle. So if I divide both sides by 4, I get 0 equals x minus 3 cubed and x plus 1 squared. Now notice the function of the squared and the cubes. This talks about the multiplicity. I'm going to get what's called a triple root of 3. And I'm going to get a double root of negative 1. Because if I were to write this 3 times, write that 2 times, set them all equal to 0, I get an answer of 3 times, and I'd get an answer of negative 1 twice. Now this talks about their multiplicity. This has a multiplicity of 3, and this has a multiplicity of 2. All right. Then we want to talk about whether the graph crosses or touches the x-axis. Well, we said earlier that if it has an even multiplicity, it touches. So this touches the x-axis, and this crosses the x-axis. All right. Next, we want to find the end behavior. And the end behavior, we want to look at the largest degree and the leading coefficient. So looking at the largest degree, if I were to FOIL all this out, which in no way I want to do, but I know this is going to have an x squared on it, that's going to have an x cubed on it, and it's going to be multiplied in the end by a negative 4. So my leading term is really negative 4x to the 5th. And if I do an end behavior on that, as x goes to infinity, then I know a positive number to the 5th is still positive, but I multiply it by a negative, I could say y goes to negative infinity. Whereas if x goes to negative infinity, and I plug negative number into a 5th power, I get a negative out, but multiply it by a negative, and I get a positive, y is going to go to positive infinity. So next we're going to go backwards. We're given the actual zeros. So we're given the solutions to the function. So we know, in essence, really, we have a 0 of negative 5, which means x equals negative 5. If I back that up, that means x plus 5 would equal 0. Likewise, I have x equals negative 1, but back that up and I get x plus 1. And it says I have a multiplicity of 2. So that means there's a second degree on that binomial. And it says the degree of my entire polynomial is 3. So notice, this is going to yield an x squared. This is going to yield an x cubed. So this is my polynomial. Now what it doesn't say is what's the coefficient out in front. That we're not going to worry about. That can almost be any number. But this is the base of the polynomial. So what I really have is I have x plus 5. And if I FOIL this out, I have x squared plus 2x plus 1. And if they wanted me to find the entire polynomial of f of x, I'd have to distribute all that through. So I'd get x cubed plus 2x squared plus x plus 5x squared plus 10x plus 5. And combining like terms, I get x cubed plus 7x squared plus 11x plus 5. And that's my polynomial. So next we're going to talk about analyzing the graph of a polynomial function In other words, taking a look at the function itself and trying to draw a picture of a graph from the equation based on what we know about the equation. We're going to do a few things. We're going to determine the end behavior, what happens at the ends. We're going to look at the intercepts, which should be the roots of the graph. We're going to take a look at the zeros of a function and their multiplicity. So that's going to be x-intercepts and how many times they're raised to certain powers. All right, whether or not the graph touches or goes through the x-intercept. All right, determine how many number of turning points we've got. All right, and based on the behavior of the graph, see what happens by each x-intercept and then draw that graph when we're done. Let's take a look at the following function. We're going to analyze this, sketch its graph based on the polynomial. So I know in this case I have x squared, x cubed, and x. So this is going to be an x to the 6th function, all right? Which means I have an end behavior as x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to negative or positive infinity, because any term raised to the 6th power is going to be positive. I'm going to start my graph over here. And what I really know is I know this. It goes up here and has to go up here, something like that. All right. Now it says I have intercepts. Well, I have an x-intercept at when this is equal to 0. Remember, set y equal to 0 to find your x-intercepts. And I have an intercept at 0, positive 1, and negative 2. Now, y-intercept I would get by setting x equal to 0. Well, when x is equal to 0, I get 0 out. So both my x and y-intercept are at the origin. Now, I know I have some multiplicities. I have a multiplicity of 2 at x equals 0. So I know it's only going to stay on the same side of the axis at this point. I know it's going to cross the axis at 1 because I have a multiplicity of 3 and cross the axis of 2. Now notice what I get from that. If it's crossing the axis and never coming back to the axis again, I know then that from 1 it has to finish high because of my end behavior. So it's going to look something like this, across the axis. Okay? I know that since it never comes back and hits the axis again, and it finishes because of the end behavior up here, then it's going to go through this point, cross the axis again. And now, at some point, it's going to bounce off this and connect over to here. The only way it does that and be polynomial at the same time is do something like this. Now, you could go ahead and graph that function, and it looks a little bit different than this. All right, we aren't going to necessarily plug in any points at this venture in time. All right, but we're going to get a general case of this. This graph actually looks, if I were to do it accurately, something like this. All right, but that's close enough to this guy over here. All right, it has the general idea of what's going on over in this graph. It's just not deadly accurate because we're not going to plug in all the points. But that's how you kind of break that down. Let's do another one. Now the problem with this example is I don't have it factored. And so you have to have command of your factoring to be able to do this. Now I look at this and some of you are going to go, there's no way I can factor this cubic. Well, you can if you use factoring by grouping. I notice in the first two, there's an x squared in common, and I'm left with x plus 3. In the last two, I have a negative 16 in common. And if I factor that out, I have an x plus 3. Now you'll notice that x plus 3 is in common. So what I have is I have an x plus 3 in common and an x squared minus 16 popping out. Now I have an x plus 3, x plus 4, and an x minus 4. Each of these has a multiplicity of 1 because it's raised to the first power. I have intercepts at -3, -4, and +4. I'm going to start graphing this. I also know that I have an x cubed graph, which means end behavior as x goes to infinity, y goes to infinity, as x goes to -infinity, y goes to -infinity, which means over here, my graph, as x gets bigger in the negative direction, y gets bigger in the negative direction. As x gets bigger in the positive direction, y gets bigger in the positive direction. So those are where I'm going to end up. Let's put in our intercepts. Here's a 4. Here's a -3. And here's a -4. It's going to cross the axis at all points because my multiplicity is 1. I'm going to find out what my y-intercept is. It ends up being -48, way the heck down here. Because I set x equal to 0, get out -48. Again, this graph's not going to be to scale, but it'll be a general idea of what's going on. I know I have to go from -48 to this intercept. So I go here, through that point, and up. From -48, I have to go over here to this point because it hits that axis. It crosses the axis because I have a multiplicity of 1, and it must come back to this axis again at -4 because that's another intercept, and it crosses and ends up here. So it looks like some form of a cubic. Obviously not totally accurate, but if this is a cubic, I have no more than 2 turning points. Turning point here, turning point here. And I've drawn a representation of what this could look like. Not, again, totally accurate, but it's a representation, and we've basically broken down the polynomial from the given function and gotten a graph from it. Don't forget to go to my math lab, do the questions for lesson 13, and fill out the survey below. See you tomorrow.